Hello everyone, and welcome back to the Panthera-HT 6-axis robotic arm quick start tutorial series. In the last episode, we set up the SDK environment, got the basic control, gravity compensation, and keyboard control scripts running, and took a first look at the overall project structure and core APIs. Today is episode 2. We'll start by walking through drag and teach, trajectory replay, and dual arm leader-follower teleoperation, then look at the code to understand the fundamental control logic behind each of these. Let's take a quick look at what's covered this episode. Part 1 is drag and teach and trajectory replay. We'll first see how the arm can be manually guided through a motion, then watch it stably reproduce the recorded trajectory. Part 2 is dual arm leader-follower teleoperation. We'll demonstrate how the follower arm tracks the leader arm in real time as a person operates the leader by hand, and walk through the code logic behind it. Part 3 covers the SDK implementation concepts. Building on the scripts from this episode and the last will help you understand the fundamental control logic that makes all of this work. As with the last episode, we'll see the results first, then get into the implementation, so you build up the big picture before diving into the details. First, we run the trajectory recording script and observe the drag and teach result. We manually guide the arm through a motion sequence while also controlling the gripper to pick up the target object. Throughout this process, the program continuously logs each frame's joint positions, velocities, and gripper state. Once recording is done, we stop the script, filling the output file path in the trajectory replay script, and run it. Before playback begins, the arm first moves to the starting point of the recorded trajectory, then re-executes the entire motion sequence in the same order and timing as it was recorded. And that completes the full cycle, from drag and teach to trajectory replay. Now let's look at why the arm can be freely dragged during recording. In the recording script, the program first reads the arm's current joint positions, velocities, and gripper state. It then computes gravity compensation and friction compensation, making it easier for a person to move the arm from its current pose. When the arm enters drag mode, the joint control uses the 5-parameter MIT control interface. Here, both stiffness and damping are set to 0, only the compensation torque is retained. This means the arm won't actively resist or pull back toward any target position, which is exactly what you want for drag and teach. The same approach applies to the gripper, so during recording, not only can you physically drag the arm, but gripper actions are captured as well. Now let's look at why playback reproduces the motion so reliably. Looking at the recorded file, you'll see it doesn't just store joint angles, it also records timestamps, positions, velocities, and the full gripper state at each frame. During playback, the program steps through the recorded trajectory frame by frame, following the original timestamps. Joint playback uses the position velocity control interface, which is better suited for stable reproduction and helps the arm reach each target precisely. Gripper playback continues to use MIT control, so the gripper actions are replayed in sync with the rest of the trajectory. Now let's look at dual arm leader-follower teleoperation. First, make sure the wiring between the two arms is correct. CAN 1 connects to the follower arm, CAN 2 connects to the leader arm, and the correct serial ID values must be set in the YAML config file as shown on screen. In this setup, one arm acts as the leader and is operated directly by hand. The other arm is the follower and tracks the leader's motion in real time. If the previous demo was record first, then replay, this one is operate and sync simultaneously. Let's walk through how this is implemented in code. The program begins by reading the leader arm's current joint positions and velocities. These two data streams are exactly what the follower arm will track. The follower arm's velocities are also read, used to compute friction compensation. Next, the gravity torques of both arms are read simultaneously to compute gravity and friction compensation. The goal is to cancel out the effects of the arm's own weight and joint friction so that control feels lighter and more stable. On the leader side, MIT control is used again. Stiffness and damping are largely set to 0, with only the compensation torque retained, so when a person moves the leader arm by hand, it feels easy and natural to guide. Let's briefly go over the MIT control formula. Kp and Kd are the position proportional gain and velocity derivative gain respectively. AFF is the feed-forward acceleration, and AREF is the reference acceleration. In the torque calculation, I is the moment of inertia, generally a constant, so AREF effectively represents the reference for the desired output torque T. Similarly, AFF is equivalent to the manually added feed-forward torque. So when both Kp and Kd are set to 0, the desired torque equals the feed-forward torque, which in this context is the leader torque. Once the follower arm has the leader's position and velocity, it continuously sends control commands with the leader state as its tracking target. This means as soon as the leader moves, the follower doesn't replay it after the fact, it follows in real time, every control cycle. The same control logic applies to the grippers. The leader gripper's position and velocity are read and sent to the follower gripper, so whatever the leader gripper does, the follower gripper mirrors it in sync. The code also includes the conceptual groundwork for force feedback, feeding the torque differential measured on the follower arm back to the leader. This script currently defaults to the smoother no force feedback mode, so what you're seeing here is focused on stable, natural leader-follower tracking. From here, adding force feedback, remote teleoperation, or more complex dual-arm coordination is simply a matter of extending this same foundational pipeline. One last point that's fundamental to understanding all of these scripts, whether it's ②Teach or dual-arm teleoperation, the program isn't just sending a single command and finishing, it runs in a loop, continuously reading state, continuously computing, continuously sending control commands. That's why the motion looks smooth and fluid on screen. Control is constantly being updated, not executed in discrete stops and starts. Looking at the high-level library, you can see that while each script produces a different result, all of them are ultimately built on the same combination of state reading and control interfaces. So the key for takeaway is that even the more advanced features are ultimately composed step by step from the basic building blocks you already learned. In this episode, we focused on ②Teach with trajectory replay and dual-arm leader-follower teleoperation. Through these two scripts, you can see how the state reading and control interfaces from episode 1 combine to produce more complete, real-world application behavior. If episode 1 was about getting the arm moving, episode 2 is about seeing how the arm can be operated and taught naturally by a person and how it achieves real-time synchronization in a dual arm setup. Next episode, we'll move into robotic arm kinematics, focusing on forward and inverse kinematics. Given a set of joint angles, how do we compute the end effector pose? And given a target pose, how do we work backward to find the corresponding joint angles? See you next time!